Another example here, we have an amplifier circuit again. V input is connected towards the emitter. V output is taken from the collector. So again, this is a common base amplifier. The third terminal is the common. So it is given here, the value of R pi is given, Ro is given, so you don't need to solve any DC analysis. We'll go directly to the AC analysis. In the AC analysis, always start the circuit from V input. So usually you start plotting the circuit carefully, because this is the most important step. If you do a mistake in plotting the circuit in the beginning, everything will be wrong. So you have to be careful in this step. Plot the circuit, start from V input. Then you have a resistance Ri. So let's call it Vi. You have a resistance Ri. Okay? Then a capacitor that is short circuit, then a resistance to the ground. Capacitor, short circuit, then a resistance to the ground. It's called R4. Then this point is connected to the emitter. We have the emitter of the transistor. Okay? So this is the emitter of the transistor. Then let's put the transistor as we have here. This is the emitter, base, collector. The collector will be connected by resistance R3 towards ground again, because the DC supply will be deactivated, will be grounded. So the collector will be connected towards the ground by R3, and then the collector also has another branch, short circuit, and then resistance R7 towards the ground, short circuit, and then a resistance R7 towards the ground, and this is the where we take our output from. The base has three branches. It's connected by R2 towards the ground, R1 towards the ground, and then we have short circuit towards the ground. So you can imagine that the base is connected by three branches. R2 towards the ground, R1 towards the ground, and then the capacitor will be short circuit towards the ground. So basically, this short circuit will cancel both resistors. Both resistors will be useless here because they are short circuited. So you can remove these three branches together and you replace them with a short circuit to the ground. Again here, the model that is more efficient for your solution, that makes your solution easier here, is the T model. Why? Because in the T model, you have the base with a wire. So you will have now the base connected by a wire to the ground in the middle of the circuit, so you can separate the circuit into two parts. So now, if you use the T model, you can replace your transistor with a resistance Re, dependent source here, and then the base is connected by a wire to the ground. This is your collector, okay? And if this is the current IE, then this is alpha IE, okay? Now, the circuit is very easy to analyze. Why? Because now you can separate the circuit from the middle. So you can plot the circuit like this. Dependent source, alpha IE towards the ground, and then this resistance, you can make it vertical for familiarity, RE, and the current IE is going up. So now this is a very easy circuit to analyze. We need to again to calculate R input looking at directly at the emitter. So here we need to calculate R input from here. We need to calculate R output directly at the collector. So R output from here. Okay. And we need to calculate the voltage gain, V output over V input. So R input, once we do this circuit, you will notice that R input is very easy. R input is Re. And of course, R pi is given. You can convert between R pi and Re very, like in a simple way. We know that R pi is Vt over I base. We know that Re is Vt over IE, and the relation between IE and I base is 1 plus beta. So you can replace IE by 1 plus beta I base. This will give you R pi over 1 plus beta. So Re is R pi over 1 plus beta. It's usually very small. Re is very small. So R input here equals Re, very small resistance, which is again bad. This is a disadvantage because usually for any amplifier we want the input resistance to be high. Here, as we noticed from this example and the previous example, the input resistance is low, right? So this is a disadvantage of this kind of amplifiers, of the common base amplifiers. Okay. Next, we need to calculate V output over V input. So again, V output equals what? Let's try to see here. V output, you can use alpha IE or you can use GM VBE. Which one is easier? Which one is easier? Think about it. For me, I think that using GM VBE, it might be easier. Why? Because in the other circuit, we need to get a ratio between VBE and V input, right? It's easier than finding a ratio between IE and VI, or getting a relation between VI and IE. It's easier to get a relation between VBE. VBE, by the way, it's in this direction. VBE is the voltage here between the base and the emitter. This is the base. Base is the ground. So VBE is the voltage between the base and the emitter, where the positive towards the base and negative towards the emitter. It's easier to find the relation between VBE and VI, easier than between IE and VI. So it's easier now to write the current source here as GM VBE. And we can say now that V output over V input, we can obtain it as V output over VBE multiplied by VBE over V input. V output over VBE equals, or let's say V output equals, V output from this part of the circuit equals the current here, GM VBE, multiplied by the total resistance, which is R3 parallel with R7, right? So the total current, GMVBE, the dependent source, GMVBE, multiplied by R3 parallel with R7. But the current is going from the ground up. The current direction is from the ground up, so the voltage will be negative. So V output over VBE equals negative GM multiplied by R3 parallel with R7. Then VBE over V input, VBE over V input, it's a voltage divider rule. It is equal to this resistance, the whole thing here, divided over the sum. But with negative sign. Why with negative sign? Because when you do voltage divider rule, you will get VEB, not VBE. You will get the voltage, VEB, the positive up and the negative down. This is the voltage divider rule. But now we need VBE. VBE is the positive down and the negative up, so it will be negative. So VBE over V input, it's negative, the voltage divider. Negative what? Negative R4 parallel with RE over, this is the resistance that you are going to see here, over the sum over RI plus R4 parallel with RE. Now, we multiply these two quantities, we get V output over V input, it will be the multiplication, negative GM R3 parallel with R7, multiplied by negative again, so negative again will make this positive, R4 parallel with RE over RI plus R4 plus parallel with RE. As you see here, again, one of the properties that we saw in this example and the previous example is we have Ri, the source resistance, the input resistance of the source here. If the input resistance of the source is high, the voltage gain will be low. If the input resistance of the source, if the source of the resistor here is high, then you will get a very small voltage gain. If this resistance is low, if this resistance is close to be zero, then no problem, you will get a very good voltage gain. So you can get a very good voltage gain here if the input resistance of the source is small. But if the input resistance is high, the voltage gain will be very small. You can increase the gain by increasing R3, the resistance of the collector and the load. You can increase the voltage gain by increasing the collector resistance. Okay? You can increase the gain by increasing R4, which is the resistance connected to the emitter, by increasing R4. Okay? So you can increase the gains by increasing the resistor of the emitter, the resistance of the collector, but if the input resistance of the source is high, this will decrease the gain very much. Now the last part, we need to calculate our output looking at the collector. Of course, since we are calculating our output looking at the collector, we need to remove everything before, forget everything before, and we look at the collector. You deactivate the source here. When you deactivate the source here, what happens? Everything here will be zero. IE will be zero, VBE will be zero, everything will be zero because we don't have any source here, right? So everything will be zero. And this, the dependent source here, again, alpha IE, if IE is zero, then the dependent source will be zero, which means it's a current source, which means it will be open circuit, so our output will be infinity. You will see open circuit in front of you, so infinity. So the output resistance here is high. The output resistance is very high, which is again a disadvantage. It's a disadvantage. The output resistance looking directly at the connector. Of course, if you look before RC, the output resistance before RC will be RC. So if you increase RC to increase the gain, if you increase RC to increase the gain, here RC is called R3 by increasing R3. So our output will be R3 if you look at before this resistance, okay? If you look after this resistance, our output will be infinity. So the output resistance can be increased by increasing, the output resistance, if you increase R3 to increase the gain, the output resistance is going to increase, which will make the output resistance of the amplifier high, which is a disadvantage, right? So if you try to increase the gain here, by increasing R3, this will increase the output resistance, which is bad thing. Okay? So in general, from this example and the previous example, we learned some properties about the common base amplifier. First, it's a non-inverting, so all the gains will be positive. All the gains, the voltage gains will be positive. It has a current gain of almost unity. What is the reason for that? Because for the common base, the input goes to the emitter and the output from the collector. The emitter current and the collector current, they are almost the same, right? You remember from our study of the transistor, the collector current is alpha IE, it's 0.99 IE. So the current gain is approximately unity, almost unity. Okay? However, if you connect some resistors, the current is going to divide between those resistors until the gain will be decreased. Like the previous example where we get the current gain to be 0.6 because the current was divided between several resistors, right? But in general, if you look at the current gain between the current of the collector and the current of the emitter, it's almost unity, it's alpha, 0.99, okay? You can get large voltage gains. However, the gain depends on the source resistance, as we explained. If the source resistance is high, the gain will be very small. The common base amplifiers, they have very low input resistance. The input resistance, which is usually RE or RE parallel something, RE is very small usually. So the input resistance is small, which is again a disadvantage. Okay? So we cannot use it as a standalone voltage amplifier. Usually we use it as one stage and we connect other stages with it in order to make the input resistance high enough. Okay? Common base amplifiers, they have high output impedance, as we explained, high output impedance, which is again a disadvantage. So the impedance, whether the input impedance or the output impedance, both of them, they are bad. They are considered to be disadvantages for this amplifier family. Okay? However, we can use the common base amplifier as a current buffer. Not voltage buffer, current buffer, where we receive a current at a small input resistance and we deliver it at the output at a high output resistance. This is a useful thing. If the input resistance is low, is small, then it will take most of the input current. And if the output resistance is high, then it will deliver most of the current at the output. So we can use it as a current buffer, not a voltage buffer. Current buffer, it needs the opposite requirements of the voltage buffer. It needs small input resistance and high output resistance. So we use it sometimes as a current buffer to receive the current at small input resistance and deliver it at the output at high output resistance. See you in the next video with more examples.